So this is question number 4. It appeared on the AB and the BC exam in 2015, and they start you off with this differential equation. And what they ask you to do in part A is they ask you to sketch a slope field for the differential equation at the 6 points that were plotted here. And so this is pretty simple to do. It's a little clunky to build a slope field by hand, but if you started in the upper left right here at the point 0, 2, when you put 0 in for x and 2 in for y, you get 0 minus 2. So this line segment right here is supposed to have a slope of -2. And that's how you're going to determine what types of line segments to draw out the rest of those ordered pairs to. Once that is wrapped up, the slope field should look something like this. So pretty quick, pretty simple, just a little clunky. In part B, it wants us to find the second derivative in terms of x and y. We want to then determine the concavity of all solution curves for this differential equation that sit in quadrant 2, and then try to explain why we feel that way. So to find the second derivative, you've got this equation right here. If you do the derivative of the left side of it with respect to x, that's going to generate a second derivative for you. If you do the derivative of the right side with respect to x, the derivative of 2x is easy. It's just going to be 2. The thing you have to be careful of is that you're doing the derivative of y with respect to x. And that's going to require some implicit differentiation. The derivative of y with respect to x is dy dx. Now this is a form of the second derivative, but it's not in terms of x and y just yet. To get this in terms of x and y, we've got to somehow get rid of this dy dx, because right now our second derivative is in terms of dy dx. So it's pretty simple to get this to be written in terms of x and y. We know dy dx equals this, so we can just put 2x minus y in place of dy dx. The thing to be careful of there, make sure you use a set of grouping symbols, because you're going to have to subtract the two terms that replace dy dx whenever you make that swap. When you distribute in, you end up with this for your second derivative in a simplified form. So here's your second derivative in terms of x and y. And then it wants us to figure out what's going on with our solution curves in quadrant 2. Well, if you think about quadrant 2, quadrant 2 up here has x coordinates that are negative and y coordinates that are positive. So if x is negative, if we put a negative right here, -2 times a negative makes this term become a positive term. And then y is positive, so 2 plus something, since it's a negative times a negative, and then plus another positive value, that's going to indicate that our second derivative is always positive in quadrant 2. And when the second derivative is positive, that's going to mean that your curve is going to be concave up wherever you see it in quadrant 2. Part C tells us that f of x is a particular solution to the differential equation, and it has the condition when x is 2, y is 3. We want to determine if we have a relative min, a relative max, or neither at this x value of 2, and then to give a reason for our answer. So normally what you would do to determine whether or not you have a relative min or a relative max is you'd build a little sign chart for your first derivative, and you'd look to see if your first derivative goes from positive to negative or negative to positive before you draw your conclusion. Well, in this case, before we even build our sign chart, we would need to know when our derivative is 0. And if you consider this value going in for x and this value going in for y, check out what the value of your derivative is at 2, 3. The value of your derivative is 1. You don't have a horizontal tangent or a cusp on your graph at 2, 3. You've got a place where you've got a slope of the tangent line of positive 1. There's absolutely no way that you can have a max or a min at this ordered pair, because this ordered pair doesn't produce a critical number. It does not give us a place where we'd have to have a split point in our sign chart for f prime. The derivative is not 0 or undefined at this ordered pair, therefore we have neither a local max or a local min at it. Part D is kind of tricky. It's not that bad. Everything kind of falls into place if you kind of follow the proper progression here. So they're telling you that y equals mx plus b is a solution to the differential equation, and what we want to do is we want to find the values of m and b that make that true. So if y equals mx plus b is the solution to this, what I thought right away was, well, if this is my solution, I can figure out what my derivative is. What's the derivative of both sides of this with respect to x? Well, the derivative on the left gives you dy dx, right? The derivative of y gives you dy dx. The derivative of mx is going to be m, and the derivative of b is going to be 0. So the derivative of mx plus b is just m. And that should make sense. The slope of the tangent line anywhere on a line is the slope of the line itself. So if this is our solution, this has to be our derivative. So what that allowed me to do is that allowed me to equate the specific derivative for this solution, m. So I put m in place of dy dx, and I set that equal to what we have been going with, for dy dx all along, 2x minus y. Now this is obviously a pretty big issue. You've got three unknowns there. You've got m, x, and y, and that's only a single equation. So that kind of says, okay, well, you've got to get something else going on here. You're going to have to produce a little system of equations if you hope to figure out what the answer for m is here. And so, a couple of steps ago, we took a second derivative of this. And so I said maybe we can go back and utilize that again here. And when you take the second derivative of this right here, what you get is you get 0. This is just a number. It's the constant slope of our line. So the derivative of that constant is going to be 0. And so our second derivative is 0. So I equated the second derivative for this specific solution curve with what we got for the second derivative from a previous piece to this problem. And I said, okay, well, this is still an issue because I have a second equation, but I still have three unknowns. My three unknowns are m, x, and y. I still need something more. But then what I noticed about this equation right here, I can actually solve this equation for y. I can add the 2x, I can subtract the 2, and I get that y equals 2x minus 2. Well, if the relationship between x and y is right here in order to make this a solution to the differential equation, what we've accidentally just done is determine what the equation of that line is. Y is going to have to equal 2x minus 2. Does that work if we go back here? And if we wanted to double check this, we could. The m of this line right here, the slope of this line is 2. So if we put 2 here, is that equal to 2 times x minus y? Well, here's what y is, 2x minus 2. So 2x minus 2x, these are going to cancel. You distribute that negative into that, you get 2 equals 2. So this, as the equation of the line, satisfies this. And what we've just done is we've just determined the equation of the line that solves this differential equation. It's really different. We're not using separation of variables to solve this differential equation. It's kind of a thinking on your feet type of question. Here's what I'm giving you. What can you do with this next? And it kind of all fell into place here if you use some of the previous work like we just discussed.